Now we will start with the most important and the most feared topic in networks, transients. Okay. So in order to understand or solve the problems in transients, we need to first understand what is the difference between transient response and a steady state response. Okay. So whenever a system is excited, that means it is given with a voltage or a current source, then the resultant output, it is going to be the sum of a transient response plus a steady state response. Okay. This is easily understood if you take a measuring instrument. If you take an ammeter, let us say, as soon as you switch on the supply, after you have given all the connections, you are switching on the supply, then what will happen to the pointer? Here there are readings, let us say. Okay, so these are all the readings. Now the pointer, initially it was at 0. As soon as you switch on the supply, what it is going to do, let us say 2 amperes is the current it is going to measure. Then what it will do, it will swing on beyond 2 amperes and then it will swing back and forth at 2 amperes and then finally it will settle down at 2 amperes. Okay. So now this swinging back and forth about its final value, that is the transient response. Okay. And what will happen to the transient response? Will it sustain forever? No, it will die out with time. Okay. After the transients die out, then the pointer will settle down at 2 amperes. So the steady state output is the 2 amperes and the transient part is the swinging. Okay. Because if you take, for example, the angle that the pointer is traveling, let us say it is given by theta, then theta of t, that means as a function of time, if you take, it will have a transient part which is the swinging plus the steady state part which is settling down at 2 amperes. Okay. So now this transients we want to analyze these transients. Okay. For which system we want to analyze? For an electrical circuit. And what is the order of the circuit? We are dealing first with the first order. So that means only one of L or C is present. Okay. There might be more number of inductors, 1 or 2 inductors, but if inductor is present, then capacitor will not be present. If capacitor is present, inductor will not be present. Only then it will form a first order system. Now why is this so important? Why the transient part is so important? Once again, you can get the understanding from this ammeter itself. Let us say the transient, the swinging back and forth, it is going on for a long time. It is taking too long to settle down at 2 amperes. Then it is not desirable, right? We want the transient to die out as soon as possible. Okay. Similarly, there will be other characteristics like what is the maximum swing it can go, right? So these are all the characteristics that we want. So that is why we do the transient analysis. Now we will start with the source free RC circuit. What is meant by source free? It means that simply there is no source. If there is no source, then what is the use of the circuit? If there is no excitation, there will be initial conditions. Okay. Only initial conditions will be present. If you remember the Laplace domain that we have seen, the capacitor will have a voltage source if there is an initial voltage across it. Okay. So we will take the RC circuit. A capacitor is present which has an initial charge. Okay. Now the voltage across both the elements we can take as V of t. Let us take this capacitance as C and this resistance as R. Now if the current through the resistor you take as IR and the current through the capacitor you take as IC, then how will these both be related? IR plus IC is equal to 0 if you consider the node here. Okay. KCL at the node will give you IR plus IC is equal to 0. Then what will be IR? This is equal to the voltage across it divided by the resistance plus what will be the current through the capacitor? C dV by dt. Okay. Now you can apply the Laplace transform. So then what will you get? V of S by R plus C times S V of S minus V of T naught. Okay. So here we have, we will take the initial condition V of T naught, initial voltage across the capacitor. So now this is equal to 0. Okay. So now V of S, if we take out common, 1 by R plus SC is equal to V of T naught, CV of T naught. Okay. So finally V of S, you are going to get V T naught divided by S plus 1 by RC. Now back, if you apply the inverse Laplace transform. Okay. So we will abbreviate the inverse Laplace transform as ILT and Laplace transform as LT. Okay. So if you apply the inverse Laplace transform, then you are going to get V of T is equal to V of T naught e to the power minus T by RC. Okay. So you can see that it is an exponentially decaying function. Okay. So that means it is going to have, initially it will have a V T naught value, and then it will start dropping exponentially towards 0. Okay. So this is the voltage and this is with respect to time. Now here what we have done, we have taken in terms of the time domain, and then we applied the Laplace transform, and then we applied once again the inverse Laplace transform. If you wish, you can just directly get the Laplace domain. Okay. So whatever circuit we have discussed for Laplace domain, you can do in the direct manner. Now one important term here is the time constant. So what is this time constant? We will see. This gives you a measure of the initial rate of decay. Okay. That means if you take the exponential curve, you can see that this is the exponential curve. Now what will be the initial rate of decay? The slope at the initial point is nothing but the initial rate of decay. So if you draw a tangent at this point, then it will extend to this point. Now this is the time curve and this is the voltage curve, right? Now this point here will be the time constant. Now the actual definition is, for an exponentially decaying curve, there is one definition of time constant. For an exponentially growing curve, there will be another definition. Okay. So for the exponentially decaying curve, what will be the expression? The time at which voltage falls to 36.8% of its initial value. So now we will see what is this value, what is the mathematical expression of tau. Time constant we represent with tau. Okay. So if you take the first definition, measure of the initial rate of decay. So dV by dt, if you find out, what is dV by dt? This is d by dt of this, we can take V naught, initial value we can take V naught e to the power minus T by RC. So you can write here, otherwise there will be a confusion. V naught is initial value. Okay. So this, if you differentiate, you are going to get minus V naught by RC e to the power minus T by RC. Now we want the initial rate of decay, that means dV by dt at t is equal to 0. What is this? Minus V naught by RC. Now from the graph, what can you get? From the graph you can get the slope as, this initial value is V naught, right? So V naught minus 0 divided by 0 minus tau. So this is going to be minus V naught by tau. So if you compare this expression and this expression, what are you going to get? Tau is equal to RC. This is the time constant for RC circuit. Now this we have got from the initial rate of decay. Now what about the actual definition? Time at which voltage falls to 36.8% of its initial value. So you can write here, V of t is equal to tau. When t is equal to tau, you are going to get V naught e to the power minus tau by RC. Now what is at t is equal to tau? We need it to be 0.368 V naught. Okay, 36.8% of the initial value. Initial value is V naught. So this is equal to V naught e to the power minus tau by RC. Okay. So this, if you calculate, you are going to get tau is equal to RC. This is because e to the power minus 1 is equal to 0.368. This is an important value, so if you can remember, it is well and good. Okay. So for a source free RC circuit, if you know the initial value of the voltage, initial voltage across capacitor, if you know, and also if you know the time constant. What is time constant? Tau is equal to R into C. If you know these two values, then you can find out the voltage or the current through any element. Okay. So we have seen a simple RC circuit. There is only one resistance and one capacitor. There might be more than one capacitor, more than one resistor, even if the circuit is a little complicated. If you know the initial voltage and the time constant, this is for the case of source free RC circuit, remember. Okay. So then we will be able to find out the, first we will be able to find out the voltage across capacitor. What is the voltage across capacitor? Vc is equal to V naught if this is V naught. V naught e to the power minus t by RC. Okay. So we can take the same circuit once again and we can find the currents as well. The voltage is V of t here. What will be the current resistor through resistor? IR is equal to Vc by R, because this is the Vc. So you are simply going to get V naught by R e to the power minus t by RC. And from here you can get the current through capacitor as well. IC is equal to minus R. So minus V naught by R e to the power minus t by RC. Okay. So basically you can characterize the circuit once you know these two values. Next we will deal with the source free RL circuit. So here we will need to know the initial value of current flowing through the inductor. Okay. So we will discuss this, it will become more clear to you. So we have an inductor and there is a resistor. Okay. So now this is R and this is L. Now let the initial current be I naught, okay, or I at t naught you can take. So now how can you write the equation for this? You can apply the KVL here. See, in the previous case, why did we apply KCL? Because there I is equal to C dV by dt. Okay. So we express in terms of current so that we will get in terms of this differential equation. Here V is equal to L di by dt. Okay. So if we express in terms of voltage, then with voltage you will get di by dt. Otherwise you will get an integral. In that way also you can do. Okay, but this is simpler. So now this inductor, it will act like a current source. Okay. So now the current, if you take to be flowing out like this. Okay. Now what will be the voltage here? This will be VR. Now the voltage across inductor, you can take the positive polarity here, negative here, because the current is flowing, current if you take it as flowing through the positive polarity, then you can write as VL is equal to L di by dt. But if you are taking here positive terminal polarity, then also no problem, you just have to include the negative sign. Okay. So if you apply KVL here, what will be the KVL? VL plus VR is equal to 0. Okay. So if you take in the clockwise sense, this is also first positive is being encountered, here also first positive is being encountered. So both of them will be positive. Now VL is L di by dt and VR is I into R. Okay. So we got in terms of the current. Now if you apply the Laplace transform, then what you are going to get? You are going to get S times I of S minus the initial value of current plus I of S into R. This is equal to 0. Okay. So if you get I of S on one side, then what you are going to get here? I naught divided by S plus R by L. Okay. So now if you apply the inverse Laplace transform, then you are going to get I of t is equal to I naught e to the power minus R t by L. Okay. So this is the expression for current. Now what about the time constant? The time constant you can find out in the similar way just like we found in the RC circuit. But here one short form that I will tell you, here the exponential term is minus RT by L. Okay. So, this you can write as e to the power minus t by L by R. Okay. So, now whatever is occurring at this denominator, that will be simply the time constant. Okay. So, basically time constant is nothing but a value of time only. Okay. And that value of time should have the units of time, and that is what we are using here. That is the concept. See, this exponential should always have a unitless power. So, if time is in the numerator, then seconds is in the numerator. In the denominator also there should be seconds, so that the entire power is dimensionless. Okay. So, this is a basic high school concept. You can remember it. Tau is equal to L by R. Even in the case of the RC circuit, what did we get? Minus T by RC. So, in the denominator you have RC. So, you can simply write as tau is equal to RC. Okay. So, we will take the source free RC circuit on one side and the source free RL circuit on the other side. Okay. So, here what did we need to know? We needed to know the initial value of voltage across capacitor. This is initial voltage across capacitor. And what is the initial value that we need to know here? Here we need to know the initial current across the inductor, through the inductor. Okay. So, for capacitor voltage is important, for inductor current is important. Now, what is the time constant here? The time constant here is tau is equal to R into C. Okay. Now, what about the time constant here? Here tau is equal to L by R. So, now here the voltage across capacitor Vc of t, this is given by the initial value, which is V0, into e to the power minus t by tau. Okay, time constant. And what about the current? Here we need current. Current through inductor, this is given by I of t is equal to I0 e to the power minus t by tau. So, you can write L here to indicate that it is the current through the inductor.